Quantum entanglement is one of the most baffling and fascinating phenomena in physics, a connection between particles so deep and mysterious that Albert Einstein famously called it spooky action at a distance. At its core, entanglement links two or more particles in such a way that the state of one instantly influences the state of the other, no matter how far apart they are. Imagine having a pair of magic dice, roll one in New York and the other in Tokyo, instantly shows the matching result, without any signal traveling between them. This instantaneous connection seems to defy everything we know about how information can travel. According to classical physics and relativity, nothing should move faster than the speed of light. Yet entangled particles behave as if they share a mysterious bond that transcends space and time. The strange nature of entanglement was first predicted by the mathematical framework of quantum mechanics and later demonstrated in countless experiments. It reveals that at the quantum level, reality is far less local and deterministic than our everyday experience suggests. Understanding entanglement challenges our concepts of cause and effect, space, and even the nature of reality itself. It forces us to rethink how particles are connected, hinting at a universe woven together in ways we have yet to fully grasp. This story begins with the birth of quantum theory in the early 20th century and the puzzling discoveries that led scientists to this extraordinary insight. The foundation of quantum entanglement lies in the principles of quantum mechanics, a theory developed to describe the behavior of particles at the smallest scales: atoms, electrons, and photons. Unlike classical objects, quantum particles do not have definite properties until they are measured. Instead, they exist in a blend of possibilities called a superposition. When two particles become entangled, their individual states become inseparable parts of a single, shared quantum state. This means that measuring one particle immediately determines the state of its partner, regardless of the distance separating them. This phenomenon was first highlighted in 1935 by Einstein, Podolsky, and Rosen in what became known as the EPR paradox. They argued that if quantum mechanics was complete, it had to allow for instantaneous effects across space, a conclusion that conflicted with relativity. To avoid this, they suggested that hidden variables, unknown factors, must be governing particle behavior to preserve locality and causality. However, later experiments, most famously those by physicist John Bell in the 1960s, tested these hidden variable theories. Bell's inequalities provided a way to experimentally distinguish between classical local theories and quantum mechanics. The results consistently favored quantum entanglement, ruling out local hidden variables and confirming that entangled particles exhibit genuine non-local correlations. This landmark finding reshaped our understanding of the quantum world, confirming that entanglement is a fundamental feature of nature, not just a theoretical curiosity. It opened the door to exploring entanglement as a resource rather than a problem, leading to revolutionary ideas in quantum computing, communication, and cryptography. The experimental verification of quantum entanglement required ingenious setups to produce and measure entangled particles. One common method involves using photons, particles of light, because they're easy to manipulate and detect. In these experiments, pairs of photons are created in an entangled state, often through a process called spontaneous parametric down conversion, where a single photon splits into two lower energy photons whose properties are linked. These photon pairs are then sent to separate detectors located far apart. When scientists measure certain properties of one photon, such as its polarization or spin, the results on its partner photon are instantly correlated in a way that cannot be explained by any classical mechanism or signal traveling between them. What's remarkable is that the measurement outcomes are perfectly matched even when the detectors are separated by distances so large that any light-speed communication would take far longer than the observed instant correlation. This confirms that the connection between entangled particles transcends ordinary space and time. Over the years, Experiments have been conducted with increasing sophistication, closing loopholes and extending distances from labs a few meters apart to satellites orbiting Earth. These advances not only strengthen the evidence for entanglement, but also pave the way for practical applications in secure communication and quantum networks. The ability to harness entanglement offers the potential for technologies that outperform their classical counterparts, but it also raises deep philosophical questions about the nature of reality, locality, and the fabric of the universe itself. One of the most mind-bending aspects of quantum entanglement is how it challenges our classical understanding of information and reality. In everyday life, objects have definite properties whether we look at them or not. Quantum mechanics, however, suggests that particles exist in a superposition of states until measured, and entanglement intertwines these states across distance. This leads to a phenomenon known as quantum non-locality, where the measurement of one particle's state instantaneously affects the state of its entangled partner, no matter how far apart they are. This isn't just a spooky coincidence. It's a fundamental feature that defies the classical idea that information can only travel through space at or below the speed of light. Yet, despite this instantaneous connection, entanglement cannot be used to send usable information faster than light. This limitation preserves the causality principle and prevents paradoxes such as communication into the past. In other words, entanglement creates correlations but not controllable signals. This paradoxical balance has profound implications for the nature of reality. It suggests that the universe at its core is interconnected in ways that do not fit within the traditional boundaries of space and time, hinting at a deeper underlying framework yet to be fully understood. Philosophers and physicists continue to debate what entanglement means for concepts like locality, realism, and determinism, prompting fresh discussions about whether reality is fundamentally probabilistic and relational rather than fixed and absolute. This ongoing exploration challenges the very foundation of how we perceive existence, opening new windows into the quantum realm's strange and beautiful complexity. Beyond its philosophical implications, quantum entanglement has practical applications that are revolutionizing technology and communication. One of the most promising fields is quantum computing, where entangled particles serve as quantum bits or qubits capable of processing complex calculations far beyond classical computers. Unlike traditional bits that represent either 0 or 1, qubits can exist in multiple states simultaneously due to superposition. When qubits are entangled, their states become linked, enabling quantum computers to perform many calculations at once and solve problems that would take classical computers millennia. Entanglement also forms the backbone of quantum cryptography, especially protocols like quantum key distribution, QKD. This technology uses entangled particles to create encryption keys that are provably secure, since any attempt at eavesdropping disturbs the quantum state and can be detected immediately. Moreover, entanglement enables the concept of quantum teleportation, where the quantum state of a particle is transmitted from one location to another without physically moving the particle itself. This doesn't mean you can teleport people like in sci-fi, but it is a crucial step for building quantum networks that transfer information with unparalleled security and speed. These cutting-edge applications demonstrate that entanglement is not just a curious quirk of nature, but a powerful resource poised to transform computing, communication, and information security in the coming decades. The potential is vast, limited only by our ingenuity in controlling and harnessing this strange quantum connection. Despite its growing importance, managing and maintaining quantum entanglement remains a significant technical challenge. Entangled particles are extremely delicate and can easily lose their connection through a process called decoherence, where interactions with the environment disturb their quantum state. Even slight disturbances, thermal vibrations, electromagnetic noise, or collisions with other particles can break entanglement, causing the system to behave like ordinary classical objects. This fragility limits the distances over which entanglement can be reliably maintained and complicates the development of large-scale quantum networks and computers. Scientists have developed various strategies to combat decoherence, including isolating particles in ultra-cold environments, using error-correcting codes, and creating entanglement swapping protocols that extend the range of entangled connections. One promising approach is the creation of quantum repeaters, devices designed to extend entanglement over long distances by linking shorter entangled segments together. These repeaters are vital for the future of quantum communication, enabling secure data transfer across continents and even between satellites. The race to overcome these technical hurdles drives much of the current research in quantum technologies, making entanglement not just a fascinating theoretical concept, but a practical engineering frontier. Understanding and preserving entanglement pushes the limits of precision and control, and success in this arena could revolutionize how information is processed and transmitted worldwide. Entanglement's influence stretches beyond photons and electrons. It also plays a crucial role in the behavior of larger, more complex systems. Researchers are exploring entanglement in atoms, molecules, and even small mechanical objects, pushing the boundaries of how far quantum effects can scale. This exploration helps bridge the gap between the quantum world and our everyday classical reality, addressing the puzzling question of why we don't observe entanglement in the macroscopic world around us. The transition from quantum coherence to classical behavior is key to understanding this quantum to classical boundary. In recent years, experiments have demonstrated entanglement in tiny diamonds and superconducting circuits, showing that quantum effects can survive in increasingly larger and more complex systems. These breakthroughs open the door to advanced quantum sensors and new types of materials with exotic properties. Studying entanglement in these systems also deepens insight into quantum thermodynamics, information theory, and the fundamental limits of measurement and control. It may reveal new principles governing the emergence of classical reality from quantum laws. By pushing entanglement into new realms, scientists are unraveling the fabric of nature itself, connecting the microscopic quantum domain with the macroscopic universe we experience every day. This research not only expands technology, but challenges our deepest understanding of the physical world. One of the most exciting frontiers in quantum entanglement research is its potential role in uncovering the nature of space-time and gravity itself. Some physicists propose that entanglement might be the fundamental glue that binds the fabric of the universe together. This bold idea suggests that space-time geometry emerges from the pattern of entanglement between quantum particles. Instead of viewing space and time as fixed backgrounds, they might be dynamic structures arising from deep quantum connections. Theoretical frameworks like the AD-CFT correspondence, a powerful tool in string theory, illustrate how entanglement in a lower dimensional quantum system can create a higher dimensional space-time geometry, hinting at a profound link between quantum information and gravity. If true, this perspective could revolutionize physics by uniting quantum mechanics with general relativity, two pillars of modern science that currently resist reconciliation. Entanglement might hold the key to a quantum theory of gravity, explaining black holes, the Big Bang, and the ultimate structure of the cosmos. While these ideas are still speculative, they highlight entanglement's potential as not just a quantum curiosity, but a fundamental principle underlying reality itself, transforming our understanding of space, time, and existence. The journey to decode this spooky connection continues to inspire some of the most profound research in theoretical physics today. The practical applications of quantum entanglement are already beginning to reshape the landscape of secure communication. Quantum key distribution, QKD, leverages entanglement to create encryption keys that are fundamentally unhackable under current physical laws. Unlike traditional cryptographic methods, which rely on complex mathematical problems that could eventually be broken by powerful computers, QKD ensures security through the laws of physics. Any attempt to intercept or measure the entangled particles disturbs their state, immediately revealing the presence of an eavesdropper. This level of security promises a future where sensitive information, whether financial data, government secrets, or personal communications, can be transmitted with absolute confidence against interception. In addition to secure communication, entanglement plays a crucial role in developing quantum networks, sometimes called the quantum internet. These networks would link quantum computers and sensors across vast distances, enabling powerful distributed computing and new technologies in sensing and metrology. However, building such networks requires overcoming challenges like entanglement distribution over long distances and maintaining coherence, spurring ongoing innovation in quantum repeaters, satellite-based entanglement, and error correction. These advances promise to revolutionize how we communicate and process information, ushering in a new era powered by the fundamental spooky connection. The integration of entanglement into technology marks a turning point where quantum theory moves from abstract science to everyday application. Quantum entanglement remains one of the most profound and mysterious phenomena discovered by science, reshaping our understanding of the universe at its most fundamental level. It challenges classical intuitions about separability and locality, revealing a universe where particles are deeply interconnected regardless of distance, and where information and reality themselves are woven from quantum correlations. From its origins in the early debates of quantum mechanics to its current role in cutting-edge technology and theoretical physics, entanglement continues to push the boundaries of knowledge and imagination. As research advances, it promises not only revolutionary technologies like quantum computing, ultra-secure communication, and advanced sensing, but also new insights into the very fabric of space-time and the nature of reality itself. The spooky connection Albert Einstein once doubted is now recognized as a cornerstone of quantum theory, inviting us to rethink space, time, and the limits of what is knowable. In embracing quantum entanglement, we step into a world that is stranger, richer, and more interconnected than ever imagined. One where the mysteries of the cosmos are deeply tied to the invisible threads linking particles across the universe.